Okay, welcome, folks. Today we're going to dive a little bit into the history of the atom. So, it takes a lot of little twists and turns, but eventually we get to how do we know what we do know about the atom. Okay, so now before we get started, we need to make sure we understand a little bit about our elements. That when we look at our elements, each element is represented by either a one or two letter symbol. When we give the elemental symbol, the first letter is always capitalized, the second, if there is one, is lowercase. They're almost all of them at least reference the name in some way or another, but some of them are based on their earlier Greek or Latin names. So you can't always trust them. And that, for example, gold is not a G but a U because it's from aurum. And iron is ferrum. Mercury is hydrogyrum. So some of these have unusual names. But for the most part, you can trust the name to match up somewhat similarly to the symbol. Now, multiple symbols can combine. When you put these elemental symbols together, we break up their various compounds. And we'll use subscripts to represent the relative numbers of each compound. But that's neither here nor there, as we are going to talk a little bit about the history of atoms and the properties. That science, especially chemistry, has a lot of very regular laws and rules. Without these laws that could be readily observed, we would be hard pressed to know half of the information that we know. And even then, most of this stuff was found after a great deal of experimentation. So let's just say that this wasn't always easy to find. But the three major laws that almost all chemists will use in one point or another is the law of conservation of mass, the law of definite proportions, and the law of multiple proportions. The law of conservation of mass will teach us that just matter is neither created nor destroyed in a reaction. It is only transferred. That's because our elements are transferring. We are not breaking apart an element. We are not making a new element. We are swapping elements in our chemical reaction. So the early alchemists who tried to turn lead to gold by doing a bunch of chemical reactions to find the alchemist stone would not have ever succeeded, because to turn lead into gold you would have to be creating some mass or losing some mass that is not possible outside of a nuclear reactor. Now, the law of definite proportions means that the portion of each element, the numbers of each element within a given compound is constant. This will lead to a constant percent by mass, that we can trust that every compound of this type will always have a constant mass. It would be hard pressed if every lump of charcoal had a different number of carbon atoms, or the carbon atoms weighed a different amount. We'd be hard pressed if, when we did a combustion reaction, we got water that was H3O and H4O or H2O2 or H2O3 or HO5. We don't have that. We can trust that if I have water, it has this much hydrogen and this much oxygen. If I have methane gas, I have this much hydrogen, this much carbon. If I have methanol, I have this much hydrogen, this much carbon, this much oxygen. But so percent by mass is just, a percent is always the portion over the whole, the portion over the total. So the mass of an element over the mass of a compound times 100 gets us our percent. So methane is CH4. Hydrogen has a mass, a molar mass of 1. With 4 hydrogens, we have a mass of 4. Carbon has a mass of 12, so the total mass would be 16. 4 divided by 16 is 0.25. Multiply that by 100 and you get 25%. All methane is 25% hydrogen by mass. Now methanol takes methane and adds an extra oxygen. So that 16 now balloons up to 32 grams. So that same 4 is now divided by 32 and multiplied by 100. So in methanol, the amount of hydrogen is 12.5. And we can trust that it's always going to be 12.5 in methanol. And the law of multiple proportions simply states that elements will always combine in whole number ratios when they form compounds. So on the atomic level, you are never going to react with a half of an atom. You will always react with 1 molecule of methane reacts with 2 molecules of oxygen to form 1 molecule of CO2 and 2 molecules of water. If I'm reacting with methanol, I'd have 2 molecules of methanol react with 3 molecules of oxygen and 2 molecules of CO2 and 4 molecules of water. There is no way to simplify that anymore without splitting up an oxygen atom. It would be a different reaction and it would not work. So after all these people like alchemists and whatnot are playing around and they start to notice these patterns, we have all these gentlemen scientists around this time are discovering all these properties. Gentlemen scientists largely because they were usually wealthy, usually independently funded. A lot of them were tax collectors, which caused some problems during the French Revolution when a couple of them actually lost their heads. But this is how they could afford to play around in the lab when we didn't have the government always funding them. They were like, well, I'm rich and I'm bored and I like the clout I get when I get to say, look at this great new thing I've discovered. Maybe I can have it named after myself. So a lot of these people at the time were of that nature. Not necessarily all of them, but it was thought of very highly to be a scientist in that time. Well, John Dalton develops a theory that would explain these 3 fundamental laws. He creates the atomic theory. That basically the atomic theory has these 4 basic premises. That 1, matter is made up of very tiny indivisible particles called atoms. Well, the atomic theory is not necessarily unique. There was the talk of atoms in early Greco-Roman times, but it was very loose and not very well thought out at the time. But that's where atom comes from, the word atomos, which means indivisible or uncuttable. So each atom of a particular element has the same mass, but the mass of an atom of a different element is different. So if I take an atom of carbon, I can trust it's going to be weigh the same as any other atom of carbon. If I take an atom of iron, it's going to have the same mass as any other atom of iron, but the mass of iron and the mass of carbon will be different. These atoms will combine to form what we now call molecules, and when they do so, they will combine in small whole number ratios. And that makes sense if you think of atoms as being indivisible. They can't break apart, so they have to combine in whole numbers. You can't break this apart to mix them together. And atoms of some pair of elements can combine in different small whole number ratios to form different compounds. So, take for example carbon monoxide versus carbon dioxide. Two very different compounds. One is present in all of our exhalation. It's a major pollutant, a greenhouse gas, but it is also necessary for life. CO2, 1 carbon, 2 oxygens. Carbon monoxide is a toxic gas that can murder in trace amounts. It is a byproduct of incomplete combustion of fuel sources with not enough oxygen, where we have 1 carbon and 1 oxygen. Two completely different compounds, but very different properties. And that only happens because we can combine in different whole number ratios. Now, his theory was still hypothetical, meaning we don't have proof from atoms. We don't have one that we can see. We just say this matches what we know. This matches the facts that we have. We don't have a net small enough to capture our atoms. And even then, this theory is not fully correct, as we'll see that atoms are divisible. We can break down the atoms into the protons, neutrons, and electrons. But the idea is that with this theory, people start going, okay, let's go test this out, and they start doing this research further into the field, and it stimulates the science a lot. So as people try to further understand these atoms, because it's now just a amorphous blob of thought, we start to find evidence of these subatomic particles smaller than the atoms themselves. Some of these subatomic particles will have positive charge, some will have negative charges. And please note, simple physics, like charges will repel, opposite charges will attract. And the heavier an object is, the harder it is to attract or repel. Heavy objects, it's like it's trying to drag a semi-truck versus drag a bicycle. So heavy objects will be hard to move by attraction. Light objects will be easy. So around the same time period, cathode ray tubes are being invented. A cathode ray tube is simply a glass tube with 2 wires inserted on either side, and we then pull a very strong vacuum to remove the majority of the gas. So it's essentially a vacuum tube. Now, it was originally called a cathode ray tube because when we connect this to a power source, it starts to glow, and this is technically called fluorescence. It's because the cathode rays were being shot of the cathode of the power source being attracted to the anode, and these cathode rays, as they hit the glass, will cause it to glow. These are electrons. These invisible electrons, when they hit the glass begins to glow. Scientists start to do all sorts of neat experiments. It's a great party trick. They would because most of these scientists were also glass blowers, you could build your own tubes in unique shapes. You could put objects within the tube. One guy put a cross in a tube, And then when you shoot the cathode rays, the cross would absorb the cathode rays, and so part of the tube, the part behind the cross, would not glow because of that. It's kind of like a shield blocking the glass. Well, it's found in these many different experiments with the cathode rays that they are affected by magnetic fields. So you put a magnet up to it and you can suddenly deflect the rays. And they can be attracted by external electrical fields. So if I put an electrical field and run it over the tube, I can also deflect the rays. And the advantage of electrical field is I can vary it, vary the voltage, vary the current. And, well, I think it's just the voltage we want to vary, and thus change how the field is diverted. Well, so our second scientist, J.J. Thomson, was able to run this cathode ray tube experiment. So he would created two plates that's going to shoot the cathode rays. He creates a pinhole in one plate. The pinhole is just a hole small enough that it lets usually a small amount, maybe even only as individual cathode ray through. But the idea is instead of a shotgun blast shooting through, we have a intense laser beam of cathode rays shooting through. He's able to then apply a magnetic field with a constant field gradient. That's going to deflect the ray in one direction. However, he's going to provide another variable external electrical field. And this electrical field causes it to deflect in the other direction. By varying the electrical field, he's able to relate the two together, the magnetic field and the electrical field, and he's able to thus calculate the relative charge to mass ratio of this electron, and that when the two fields cancel, he can compare these to each other. That otherwise the electron would shoot off in one direction, but if you can keep it going straight by balancing them out. So now that we start to discover these cool facts about the electron, people were trying to try other ways to analyze these electrons. Now, they found they could generate these electrons with high-powered beams of X-rays, for example. Shooting X-rays at things can knock off, could essentially cause the fragmentation of atoms into electrons. So we have a scientist by the name of Robert Millikan who uses this oil drop experiment. So the oil drop experiment is a similar thing with a pinhole and plates, but instead he creates a giant oil drum. It creates an oil drum that with a perfume spray bottle that's just with oil droplets in it. Now it doesn't have to be a viscous oil, but oil that will properly disperse and nebulize throughout the chamber when it's sprayed. So he's going to spray this into there, and it's going to shoot out into tiny little droplets into this vacuum. And eventually, like all liquids, even in small droplets, will eventually be affected by gravity and descend. As they descend, they're going to fall through a little pinhole. So through the little pinhole. So they're falling through the pinhole between these two electrical plates. And on the other side of that pinhole, in these electrical plates, we have a little X-ray gun that shoots X-rays at the droplets. And he has a little view window that he can view the droplets. So as he shoots them with the X-rays, he imparts various numbers of cathode rays. He generates electrons within the oil droplets. And by varying the electrical field of the plate, he can then pull the droplets up, or let them fall slower, or even have them stop in midair, because gravity is a known force. Gravity depends only on the mass of the droplet. And so if he knows the size of the droplets and he knows mass, the force of gravity, which they did, they can figure out what they can relate that to the electrical pull that must be pulling this upwards. So because they were able to measure the field strength and figure out this, they were able to find what is the charge per electron on those droplets. So the charge of each droplet may be more than this, but the idea is that it was some proportion of this. That the charge was some proportion of 1.602 times 10 to the negative 19th coulombs. Now, you don't need to actually know this. Anytime you would actually know this is something we could look up. But the fact of the matter is that is the charge of an individual electron. Now, because our friend J.J. Thomson had already discovered the charge to mass ratio, we could then derive the mass of an electron, which is be 9.10 times 10 to the negative 28th grams. Very, very small number. Now, they knew facts about atoms. They knew the atoms were electrically neutral. So even though we're able to generate these electrons out of the atoms, the standard atom is usually neutral. So the only way to cancel a negative is with an equal amount of positive. So scientists postulated that we must necessarily have a proton with the opposite charge in there. They also had a rough idea of how many protons and electrons must be in various atoms. They had a rough idea, and they knew something about the mass of an individual atom. They may not have been able to measure out individual atoms, but they could figure out, due to reaction proportions, what an individual atom would likely weigh. And so they knew that that 9.1 times 10 to the negative 28th is much too small to account for all the mass, so that the proton must therefore be much heavier mass than the electron. So at this point, we still don't really know what an atom looks like. We know that it has a proton. We know that it has electrons, but not much more behind that. So the picture at top is maybe our atoms before, the indivisible sphere. But J.J. Thomson reasoned that since atoms are neutral and made up of electrons, they must have the source of the positive charge. And so we get this idea. The idea of that mostly positive with electrons spread throughout. So there was reason that because the electrons had very little mass, they must also be very small. So he imagines the atom as a plum pudding with positive charge, and electrons embedded like raisins in the pudding. Now, this was not the only model. There's also like a planetary model with the electrons revolving around the sun, which is the proton. And there's maybe some others too, but the idea of a good hypothesis or model is that it's testable. Now, J.J. Thomson, because of his various researches, had some clout, so his model was one that was thought highly of. And so we have the gold foil experiment. Around the similar time, radiation's also being discovered. We're figuring out that, oh, wow, hey, some atoms will break apart and shoot off these rays that can, among other things, darken photographic plates. That it is independent of an external source. They thought, like, at first, oh, hey, maybe it's sunlight that's doing it. But even kept in a dark drawer, these things glowed. Because some things, we know, you shine a light on it, they absorb the energy, and then they glow, like fluorescence and phosphorescence. Materials will absorb energy and then glow. Well, the radioactive stones will glow regardless of whether they've been kept in a dark drawer for a week or a month or a year. So they find out, oh, radiation can be generated. These guys, they naturally produce this radiation. There's several types of radiation. One similar to a cathode ray, which is called beta decay. But the main one we're going to concern with ourselves is alpha decay. It is a heavy radiation that is both massive, and that it has 2 protons and 2 neutrons, and also highly charged, where it's just 2 protons without any electrons. So Rutherford Hayes and his associate Hans Geiger of Geiger Counter fame developed this experiment to test the hypothesis of the plum pudding model. He's going to shoot alpha particles through a very thin gold foil. Now, the idea being that that gold foil could be pounded extremely thin, and so there'd be less space, we need to be able to penetrate it with the alpha particles. Alpha particles can be blocked by the thickness of your skin. Your dead skin cells can block alpha particles. So we need something incredibly thin layer to be able to guarantee to penetrate it. So that's why they used gold foil. So they surrounded the gold foil on almost 360 degree side with a photographic plate. And so the idea is, like, as they shoot the radiation through the gold foil, the deflection pattern is going to tell us about the atoms that it penetrated. So they're going to use radon gas in a box. It's going to open up, let the alpha emitter shoot off the alpha particles, and it's going to punch through the gold foil. Now, because it's thin enough, and they thought the plum pudding was soft enough, it could punch through, even though it's positive, punching through positive. And it's going to shoot to the back and hit the back plate. But what we will see doesn't always match what we expect. So, even though the plum pudding model had a large positive charge in the atom, the idea was that positive charge was so highly distributed that it was not likely to repel or deflect the alpha particles. And so while some particles did experience no scattering, they punched right through, some received intense scattering, like it hit and ricocheted off to the side. And because the Rutherford and Geiger were very methodical, they didn't just check where they thought their answer should be. They checked the entire area, and they found there's some of them even bounced back entirely. Some of them had a full repulsion. And the only way that's going to happen is if you have something very dense that can bounce these heavy particles back. So this would only occur in the collision between 2 dense positive objects. So this clearly disproved our plum pudding model. So from this, the nuclear model was developed. That the idea that these atoms are mostly empty space. So we're going to end with this slide, the nuclear model of an atom. The atom's positive charge and the majority of its mass are located in a relatively small area, which later called the nucleus, plural of nuclei. The vast majority of the atom is empty space. Small negatively charged electrons are spread throughout this empty space. The number of negatively charged electrons is equal to the number of positively charged particles called protons that are within the nucleus. So those alpha particles, for the most part, shot through empty space. They missed the nuclei and made it through. If they got too close, they could be deflected off course. But if they straight up got the bad chance of hitting the nuclei, they would bounce back, and that's what they saw in the experiment. Even then, our nuclear model is not fully done. It is not fully cooked yet, because the mass doesn't always correlate with the number of expected protons. And this is because there is a missing element there. We know a rough idea of the number of protons and neutrons that must be there, but we don't know. But we know, this is heavier than we expect. Things like, for example, hydrogen only have one proton, and the mass works pretty well. But when we get to things like say the next element down, you start to have one proton, two protons and two neutrons, and the mass starts to increase, doubling each time as we move up. We're adding a proton and a neutron both, and as we get heavier and heavier, essentially you start to gain more mass than we gain charge. So it doesn't quite match up. So Rutherford went on to postulate the presence of the neutron, the idea of an uncharged particle of similar mass to the proton that would also have to be present. So this would take us several years more before it was finally discovered by James Chadwick, which was one of Rutherford's students. But the idea is that it was predicted before it was discovered. It wasn't just a total mystery there. So, and sometimes people will miss it. Marie Curie's daughter and daughter's husband also almost discovered the neutron, but they had some interesting experiments where they saw what they thought that would later be found to be neutrons. They dismissed it. They didn't quite know what they're looking at, and so rather than publishing the data, they let it slide as an unusual result. And later James Chadwick was able to do the experiment himself, and he was able to make the connection that, this is a neutron. This is what I'm seeing. This particle flying through space that is unaffected by electrical fields. But that's where we'll stop for today. Thank you for your attention.